So, what if we could teach a machine to master a skill not by programming every single tiny step, but by just letting it learn from experience? The same way we do. Well, that's the whole idea behind one of the most exciting fields in AI today, reinforcement learning.
I mean, really think about it for a second. Nobody handed you a textbook with the physics equations for balance and momentum, right? You didn't sit there studying a perfect data set of bike rides. Well, you just tried. You got on the bike, you probably wobbled, and you almost certainly fell. And that fall, that was feedback, right? A little bit of punishment. But you didn't quit. You adjusted, you tried again, and then eventually you stayed up for a few feet. That feeling of success, that was your reward. This simple, powerful loop of trial, error, and feedback is how we learn pretty much everything.
So the big question becomes, can we sort of bottle that process? Can we actually teach machines in that exact same intuitive way? And that is precisely what reinforcement learning is all about. It's an entire field of AI that's directly inspired by this very human way of learning by doing. Okay, so let's peel back the layers and see how this thing actually works under the hood. It's a really elegant and powerful system once you see all the moving parts. So here's the formal definition. But what's really key here is that unlike other types of machine learning, there is no predefined correct answer. The system has to figure out the best moves for itself, basically by interacting with its world and learning from the consequences. And to really get it, you just need to understand 5 core components. Seriously, once you can spot these 5 pieces in any problem, you'll see how the whole system clicks into place. They are the absolute building blocks for everything. First up, you've got the agent. This is our learner, our decision maker. You can think of it as the brain of the operation. In our bike example, you were the agent. In the AI world, it's usually some kind of algorithm or a neural network. Now, the agent doesn't just exist in a vacuum. It lives inside an environment. This is the world it operates in, the thing that sets the rules of the game. For you on the bike, the environment was the pavement, gravity, the bike itself. For an AI playing a game, it's the game world and all its rules. And here come the other 3 pieces that make it all happen. So at any given moment, the agent looks at his current situation. We call that a state. Based on that state, it decides to take an action. Then the environment responds by giving the agent a reward, which can be positive or negative. And this is where the magic happens. It all comes together in this continuous feedback loop. The agent sees the state. It takes an action, it gets feedback, and boom, it's in a new state. This cycle just repeats over and over and over again, sometimes millions of times, letting the agent get just a little bit smarter with every single try. This is what makes it so different from what you might think of as normal machine learning. See, in supervised learning, you basically have a complete answer key. You show the machine a million pictures of a cat, and you tell it, this is a cat. But in reinforcement learning, there is no answer key. The machine has to figure out for itself what a good move is just by seeing what rewards it leads to down the road. Okay, but this whole process brings us to a really fundamental challenge that's right at the heart of all reinforcement learning. It's this delicate, tricky balancing act that every single agent has to perform. Think about it in your own life. Do you go to your favorite restaurant that you know is always good? Or do you risk it and try that new place that just opened up? It could be amazing, or it could be terrible. That is the core dilemma. So the classic way to think about this is what's called the multi-armed bandit problem. Picture this. You're in a casino and you're standing in front of a whole row of slot machines. Each one has a totally different secret probability of paying out. Your goal is to walk away with as much money as possible. What do you do? This is that trade-off in action. You can exploit what you already know by just keep pulling the lever on the one machine that's paid out a couple of times. Or you can explore by trying the other machines. You might lose a few bucks, but you have the chance to find a machine with a way bigger jackpot. Getting that balance right between exploiting and exploring, well, that's the secret sauce to learning effectively. All right, so that's the theory. But how does this elegant little loop build into some of the most mind-blowing AI achievements we've seen out in the real world? Well, games are the perfect playground for this stuff. And this is where things get really wild. The huge breakthrough came when researchers combined this learning loop with deep neural networks, creating something called deep reinforcement learning. This is the tech that powered DeepMind's AlphaGo. It taught itself the ancient, incredibly complex game of Go and then beat the world's best human player. Other systems learned to master old Atari games with 0 instructions, just by looking at the pixels on the screen and trying to make the score go up. I mean, that's something that was pure science fiction just a decade ago. And it is not just happening in virtual worlds. In robotics, RL is letting robots learn super complex motor skills. So instead of a programmer having to code every single tiny joint movement, they can just create a simulation where a robot can practice walking for like thousands of hours, falling down, getting back up, until it masters the skill and is ready for the real world. And believe it or not, this tech is already shaping your daily life. Those recommendation systems on platforms like Netflix and YouTube, they use these exact principles to explore your tastes and exploit what they already know you like, all to personalize your feed. It's also being used in high-stakes finance to develop trading strategies that can adapt on the fly to chaotic markets. So where's all this headed? What's the big picture? Well, reinforcement learning is way more than just another technique. It's a really fundamental shift in how we can build intelligent, adaptive systems. But it's not magic. There are still some huge hurdles to overcome. For one, it often requires a massive amount of data and a trial and error, which just isn't practical when real-world mistakes are expensive or even dangerous. I mean, think about a self-driving car. You can't have it explore by crashing into things. And getting an agent to take what it learned in one situation and apply it to a new one is still a major, major challenge. Ultimately, I think this quote just captures its power perfectly. It's a tool for making a series of smart choices over time, even when you don't have all the information. Which, when you think about it, sounds a lot like life, doesn't it? This ability to learn, adapt, and strategize in really complex, messy environments is exactly why so many researchers believe reinforcement learning is a critical piece of the puzzle in the long-term quest for more general, human-like AI. And that leaves us with a final and, I think, fascinating question. As this technology gets more and more powerful and efficient, we have to decide what we point it at. I mean, from discovering new medicines to optimizing our energy grids or managing global supply chains, the possibilities are just profound. The real question is, where do we even begin?